I spent the last few months developing a new modular form package in ParisGP. Now, of course, there exist lots of modular form packages available. For instance, William Stein did one in Sage, and Karim and Bernadette are developing one also in ParisGP. This is another one. I'm not saying it's better or worse, it's just another one, so you can play with it. So, what are the different methods that are used to compute spaces of modular forms? I'm talking about really completely standard modular forms over gamma 0 of n with character. So I listed a few, maybe I forgot some, but it doesn't matter. One of the very oldest is using theta functions. It's not very systematic, but it works. Or you can use products of lower weight forms, like that you know, for instance, Eisenstein series. And the most common method which is used is to use modular symbols or variants of modular symbols. I give the names of Manin, Cremona, Merel, there are certainly other names. So in ParisGP, there is now a package which has been developed by Bernadette and Karim. Everything starts with MS for modular symbols. So one of the main functions is MS init, as usual in Paris, like NF init and so on. And there's finally another method, which is also rather old, which is simply using trace formulas. So my package is based on that last method. So I developed, as I wrote here, a large package based on this, which you can play with if you want, even during my talk, except that you have to do the whole compilation again. The branch is called, well, it assumes you know how to use Git and get to a new branch, but if you already downloaded the whole Git thing, you should just do a Git checkout of this branch with the necessary things that you put on that line. I'm not giving a Git talk here because I don't know much about Git. But anyway, this branch does exist and works. And here, I just call, instead of calling it MS, I call it MF. Okay, well, we can change this later, of course. So the main function will be initializing the space will be MF init. For the moment, I have not finalized this branch. So instead of putting all the functions where they should be in Paris, you'd simply have to read a file, which is, of course, in the distribution, which is, of course, called MF install. So if you get that branch, you first have to do this to use it under GP, of course. And the whole explanation, well, I'm going to give you only a few explanations here, but the whole explanation is in a PDF file, which is in the branch, which is, of course, the manual. So I'm leaving this slide up for those people interested, because those are the three things that you really have to know: the name of the branch, the file that you have to read in, and the manual. Okay? So I don't have many slides. I want mainly to do a demo of the package. But still, I will explain a little the theory behind it. So we want to work in the space of modular forms of weight k over gamma 0 of n with a character and subspaces of that. So these are really the most classical of all modular forms. And when I say that I'll work with trace formulas, that's not unique, because there are many trace formulas available in the literature, even for that completely classical aspect. So the classical trace formula, which has been written many, many times with lots of mistakes, gives simply the trace of the nth Hecke operator Tn acting on the whole space, either Mk or Sk. Well, usually we use cusp forms. By the way, if there are people in the room who are used to Hecke operators, please note that I use Tn independently of the fact that little n is coprime to the level. Some people call UP the Hecke operators when p divides the level. I don't like this. It's just T. Okay, there is a very nice formula developed by Niels Skorupa and Don Zagier, which gives more than that. It gives the trace of Tn composed with the Atkin-Lehner involution WQ. Unfortunately, their formula is already complicated enough, and they worked it out only for trivial character. It would really be nice to work it out for any character, but as usual, this kind of work would not be recognized by the mathematical community, so it just simply would be useful, but nobody will do it. And more recently, and that's probably why I became again interested in this, it was noticed probably by many people, but okay, I learned only from it by Andy Booker and collaborators, that in fact you can get from the classical trace formula above, you can deduce a formula for the trace of T of n on the new space. And it's not completely clear, and in fact the proof is several pages. Of course, everyone knows that one can deduce the full space has a decomposition in terms of the new space, so you could do some kind of Möbius inversion to get one from the other. But okay, it is Möbius inversion, but very sophisticated. Well, very. The computations that you have to do are far from straightforward. So there does exist a trace formula on the new space, and that's really what led me to do this. So how do you construct spaces of modular forms using space formulas? Well, you start by using a trace, what I call a trace form. So for instance, for the new space, you simply take the generating function of the traces over the space you're interested in of the Hecke operators times q to the n. That's what I call the trace form. And on the new space, well, I'm sorry, I'm speaking to people who know this theory. I'm sorry if you don't. On the new space, it's completely trivial that this is a modular form because it's simply the sum of the eigenforms. I mean, this is trivial. I mean, there's no need to give a proof. Okay, I did not define what I call the Atkin-Lehner spaces, where you put an additional q up there. I don't have time, but it's similar, except that it's a smaller space. You do exactly the same using the Skorupa-Zagier traces, and again, it's completely trivial that it's a modular form. But what is much more surprising is you do this for the full space now. So you use the initial trace formula, which I mentioned preceding slides. So you take the generating function. And here, there is absolutely no reason why this thing should be a modular form. Because it's well known, at least to the experts, that when n, little n, is not co-prime to the index, to the level of capital N, for p divides n, for instance, the TP are really nasty operators. I mean, they're not Hermitian, they're not, I mean, they're really bad. So if you try to copy what I call the trivial proofs in the preceding cases, this is certainly not the sum of the eigenforms because it's not true. They are not, it's not true that in the full space there are eigenforms for the full space. I mean, you have to exclude the Hecke operators for p dividing n. But it is a non-trivial theorem, which I proved last month or 2 months ago. Must have been known, but I've not seen it in the literature. This is a modular form in the whole space, of course. So you have several methods to, so as I say here, this is not trivial because the Hecke operators create problems. So you have several methods now to compute modular form spaces. You can either start from this form and build the space from it, or you can start with the new form, the new trace form, construct the new space, and then the old spaces from it. Okay, you have several methods, but it's quite remarkable that you can do it directly without going through the what's called the new space, which is no. It varies, and I have implemented both. Both are available to you in the package. You can either go directly with this form or go through the new space. And I have examples where one method is faster, and I have examples where the other method is faster. We can talk about this. So once you have the trace form, of course, to construct the space is not difficult when you know the theory. First, you range through all the divisors of the level, and then you range through the divisors of n over m. You apply Hecker operators, you apply expanding operators, tau gives d tau, and you generate the space in this way. And of course, once you have a generating system, you extract from this a basis. In practice, you don't do it like that. You add one form after the other until the dimension is reached. And you can limit the number of terms of the Q expansion that you take by using what's called the Sturmbaum, which tells you how many terms you have to take. Okay, once you have a basis for the space, you can do you can play with it. Of course, the main thing that you want to do, that users in modular forms want to do, is to get the eigenforms. This time we're in the new space, so eigenforms for all Hecker operators. And this is done by a procedure which I call Galois Splitting. Once again, I don't have time to explain in detail, but in the examples that in the demo that I'll give, I'll show you. You have to use the full Hecker algebra, what's called the Hecker algebra, and not just the Hecker operators. For instance, well, I'll show you an example. You need the eigenvalues of the Atkin-Lehner operations. You need to compute them. And the more difficult thing is to get the Q expansions of the modular forms that you have elsewhere than the cusp infinity. And that's a difficult problem. One can use the Atkin-Lehner involutions to do this, but only for the cusps such that the GCD of C and n over C is equal to 1. In particular, if the level is square-free, it's okay. But if the level is not square-free, it's a non-trivial problem. Now, the use of modular symbols normally is much better for this kind of thing. Normally, modular symbols should allow you to compute Q expansions at all the cusps simultaneously. But, okay, that's not my talk. Okay, that's my last slide. I worked up to now with the trace form for the space of cusp forms. Now, in addition, in modular forms, you have Eisenstein series. And surprisingly, the space of Eisenstein series is really completely explicit. I mean, Eisenstein series are the objects, almost the simplest modular forms that you can construct. And I didn't find it in the published literature. There is a thesis of somebody called Weisinger from 1977, which apparently has never been published, which gives an explicit basis of Eisenstein series. But I repeat, if you can give me a reference either than this, elsewhere than this thesis, okay. Anyway, it's completely, it's extremely simple. The proof is not so simple, but the basis itself is simple. And of course, I implemented this. And the second thing, which is much more fun, is modular forms of weight 1. It's well known to the experts that computing modular forms of weight 1 is a difficult problem. And in fact, as far as I know, they have been computed only up to level 1 or 2,000. So very small. So I implemented an algorithm which is very pretty. In fact, the problem that I asked you of linear algebra comes exactly from this, from George Scheffer. I can explain it this afternoon to people if they're interested, to compute modular forms of weight 1. But I have implemented this method in the package. But for now, the implementation is quite bad, in particular because of the problems I mentioned, but not only. So you can't really go above level 200 or 300. So I'm not yet at the point where I can go over the bound that I mentioned, 1,000 or 2,000. And finally, I implemented on the, because I was asked by Francis Brown, who is working on multi-zetas, I implemented a search algorithm. If I have time, I'll show you. So you just give A2 and A3, for instance, and it gives you, and you give it a range of levels, weights, and so on, and it gives you all the modular forms, all the eigenforms with integer coefficients having the given A2 and A3 or A5 or whatever. Okay, so I think that finishes my slides. And now I'm going to sit at the computer and show you a few examples. Are there questions? Okay, so I'm in a directory which I call Paris MF trace because that's where the branch is. So I'm in the branch Henri MF trace, and as I said, I launch GP, and the first thing I do is to read this file mf install. What? Sure. Okay. Now, it does not only install things. In fact, here it also computes all class numbers up to 210 to the 6, which I will need for the demo. You can compute them up to whatever you want. Okay, so, excuse me?
I'm trying to use it, it doesn't work for me.
Why?
It says it can't find a single MF2.
You need to reload configure. Reload configure minus N if you like. Otherwise it won't work compile some file.
So as I mentioned, the basic command is mfinit. So let me start with mfinit level 26 weight 2. I don't put anything behind. Of course, there are many other parameters in the mfinit command. The next parameter, for instance, would be to say which character I take. So if I don't put anything, it's the trivial character. Then there is a flag saying whether I want the new space, the full space, and if I want to split it and so on. If I don't put anything, it means that it's the new space and I want to split this space. So if I write, for instance, if I want to look at the, well, first if I want to look at the dimension should be mf.dim, but I didn't do this, it's simply that. But there is, in fact, a simpler way to do it, is to ask for mf-gal pulse or mf-gal dims. Well, in this case, it's essentially the same, of mf. It answers ZZ, which means that both spaces are rational. And if I want to see the Q expansion, I ask for the series expansion of the basis. And it gives you the two eigenforms generating the space. If you don't see them properly, here are they separately. Here's the first one, and here is the second one. So these are the two eigenforms of level 26, weight 2. I can, of course, do lots of operations on this. To take a completely different example, I will initialize the space of level 1 and weight 24, which is well known also. And now if I do this, it also has dimension 2. And if I ask for the series expansion, well, it tells me that there is only one form, but in fact it's a cheat, because this form, you see, has coefficients. The coefficients belong to a number field of degree 2. So in fact, for each embedding of this number field, you have one modular form. So in fact, the fact that you have a number field of degree 2 means that you have two conjugate eigenforms, depending on which embedding that you take. So the dimension, in fact, if you ask for the dimension, it will give you 2, of course. But here is specifically the eigenform itself. By the way, it ends with q to the 16, but of course I could ask for the q expansion to the as many coefficients as you want. Now, this polynomial you may not well, reasonable number. Essentially, it depends on the size of the table of class numbers that you computed. I computed by default up to 10 to the 6. So that means that I can get roughly the square root of that. I can get 1,000 coefficients with no cost. And if I want more, then I'll have to compute more class numbers. But if you ask, and the table is not big enough, of course it computes the necessary class numbers on the fly, but then it's much longer. If I take this polynomial z squared minus z minus 36042, of course, you will recognize if I ask for the discriminant of this polynomial, modular form experts will recognize immediately this number, which is not a square, contrary to what it looks. It's a prime number, 12 squared, 13 squared. It's a well-known number in the theory. Okay, I was talking of the Hecker algebra. So, for instance, if I try to split the modular form space at level 512 and weight 2, if I tried to split it using only the Hecker operators, it would fail, because the operators cannot split that space. It's a theorem. So I need really the Hecker algebra. And let me show you exactly what it does. So it finished immediately. The dimension of the space, well,
Single operator.
yeah, a single operator. I need combinations. So
Do you have an example where you need more than, so for instance, we only use sums?
yeah, for the
operators. Do you have other examples?
I do not have other examples, but they certainly exist. No, of course. Now, here, let me show you the Galois, because that's really the most interesting thing. So it tells you that the space, if I expand the series, the eigenforms, then in the first 1, 2, 3, 4, 5, 6 subspaces, I'll have eigenforms over a quadratic field. So that's the quadratic field in each case will be q squared 2. Why not? And the last space, and that's exactly on this last space that I'll have problems, this last space is in fact irreducible. So it will, z4 minus 4z squared plus 1 is an irreducible polynomial. So here the coefficients will be in that number field. And let me show you, in fact, why this is true. I can ask for something called MF Hecker, Matt Hecker, I think. Matt Hecker of MF, and I'll ask for the Hecker operator, let's say at 5. So it gives me a big matrix. Of course, it's a 16-dimensional space, but that's not what's important. What's important is to take the characteristic polynomial of this and factor it. Okay, and you see that's absolutely characteristic of the things which don't, which are bad. Everything has a square. The powers are 2, 4, 2, 2, 2, 2. So I can split my space, of course, in 5 pieces corresponding to x minus 2 squared, x to the 4, and so on. But once this is done, I can't go any further. I can do the same with the Hecker operator T7, for instance. Okay, once again, and again, if you factor it, you see, you only have squares. If you do it with 3, it looks better. If you do it Hecker operators at 3 and factor the characteristic polynomial, you do get ones, but you still have even exponents. Okay, I can't show you, of course, the whole detail, but you can try 3, 5, 7, whatever. It will never completely split the space. On the other hand, if I take the Hecker operator T3 and plus the Hecker operator whatever, T5 probably. Okay, I get, of course, the sum of the two matrices. And now, if I do this, I'll get 1, 1, 1. I still have squares, of course, but in fact, the spaces which were not able to cut now will be cut. Okay, I'm just showing you this. Okay, what can I... Okay, I can ask, for instance, let me do something else. MF init of, let's put ourselves in level 121 to have something a little bad. MF Galois of MF, well, it's all rational, so I can ask for the series expansion if I want. Here it is, who cares? But now what's more interesting is to ask for the action of the Atkin-Lehner operators on MF. So the Atkin-Lehner operators are defined on what are called primitive divisors of the level. So 121 being a square, there are only two primitive divisors, 1 and 121. So for 1, it's not very interesting, because of course the Atkin-Lehner operator at 1 is the identity, so it will tell me that the eigenvalues are 1, 1, 1, 1. Yeah. Well, I could make a script giving me this without writing anything. On the other hand, at 121, it's non-trivial. Now, when the Atkin-Lehner divisor divides exactly, when there's no square, there is a formula. You can just output the formula. But when it's a square, of course you can't see it because it's going to be rather fast. But when there is a square, it really has to work. Here it's working, but it was almost immediate anyway, because we're in a low level. If I tried it with 11 cubed, it would take a few minutes. And you see that the Atkin-Lehner eigenvalues, well, whatever they are, -1, -1, -1, -1. Okay, to finish my talk, well, of course I can play with examples that you ask me. I'll show you the MF search thing. So I want to search for modular forms in a certain box. So the box is, you can give it in many different ways, but for that you have to read the manual. I'll just do the most stupid way, which is that the product of the level and the weight is less than a certain value. And the value that you give here is 1/2 of that value, because the level is assumed to be even. So if I put, for instance, 50, that means that it will search in a box where the product of the level and the weight will be less than 100. And then I put, here again, there are many different formats. If I put the most stupid format, which is simply a vector, this vector will simply be, by default, A2, A3, A5, A7, and so on. But I could, of course, put instead bracket 2 comma something, bracket 5 comma something, if I don't want the 3, and so on. There are many different formats. Let me just show you the most simple. So I ask that A2 is equal to 1, for instance. A3 is equal to -1. I put at random. Of course, if I put values which don't exist, I'll have the empty vector. And here it tells me how many things are there. It tells me that there's 5 eigenforms of this type, and it gives me a few terms of the Q expansions. Of course, I can ask for more, and you can read. You see, if you can, I'm sorry, I don't point it out. 33.2 means it's level 33, weight 2. 39.2, 42.2, 52. It's all weight 2, but if I had taken another example, you could have weight 4 and so on. Now I'm going to be more restrictive. I'll ask A2 equal 1, A3 equal -1, and A5 equal, for instance, well, here I have an A5 which is -2. So if I do that, well, I get a subset, of course. Now I only have 2 of these things. And I'll ask for A7, and let's see, A7, the first one has a +4, the other one has a -1. So normally, I hope, if I ask for 0, for instance, it should give me the empty set.
Okay. If you put nothing, you put the empty set. If you have no conditions, you put the empty set.
Okay, that's a bug or a feature. If you put no condition, it should answer all the modular forms. Okay, I'll look at that. Okay, yes?
Or you can get more.
I think that you just do comma 50. No, it doesn't work. Okay, sorry. Or comma 50? No. Okay, sorry. I'll have to. If you change the default series, okay, I'll answer that later. I have to look at the code. Okay, I finished my talk. Thank you.